Review for exam 3 here in Prob and Stats has been mostly about statistics, though we started with some statistics in chapter 7 especially. That was pretty theoretical and involved a lot of ideas from probability. But we did start with chapter 6. Not a ton of time spent on chapter 6 in class, but I had you read it. There were a bunch of things about graphs in there, making histograms, for example, making box and whisker plots, making stem plots. Had some of those come up on homework as well. Should certainly be able to make a stem plot, and you should certainly be able to read a histogram. I don't typically test on these things, but I'm not ruling it out. As far as a box plot goes, a box and whisker plot, the book's got kind of a complicated procedure that involves inner and outer fences, and I'm like, that's a little bit too much for us. You could just do a simpler 5-number summary box plot where you would want to make an axis for a scale. Maybe the axis happens to be this scale. I'm just making something up here. And maybe the minimum of your 5-number summary is 7, and the first quartile is 11, and the median is 13, and the third quartile is 19, and the maximum is 26. That would be a box and whisker plot, or just a box plot for short, showing you the 5-number summary, the minimum, first quartile, which I use a lowercase q for, the median, just a plain M, the third quartile, which I like using a capital Q for, and the maximum that I'd like to do in capital letters. That's just for fun. Okay. Showing you a quick picture of the distribution. And if I had made this maximum even further away, it would be clearly a right skewed distribution in that case. I have made the third quartile further from the median than the first quartile is, making it somewhat right skewed. Not ruling putting that out on the exam as well, but you should also be able to read a histogram and possibly make a stem plot, a stem and leaf plot. More importantly, we talked about statistics, population parameters, samples, and statistics. And in particular, some particular statistics, the most important of which is the sample mean, capital X bar. What is it? Based on a random sample of size n from a distribution, capital X1 through capital Xn, it is this formula. Remember that for us in this more theoretical probability and statistics course, when I use capital X1 through capital Xn, that's a random sample. That means it's a collection of independent and identically distributed random variables, IIDRV, independent and identically distributed random variables. These random variables all have the same distribution. Maybe they're all gamma random variables. They're assumed to be independent. Why? Because we want to assume it so that we can do things. When you apply this theory, you have to actually do actual random sampling in real life. That's actually harder. Like, how do you actually do random sampling in real life? You need some randomization procedure. You need, if you're doing a survey, people that actually have to respond to your survey and not blow you off. So it's harder to apply this than it is to do the theoretical math, actually. But this is a statistic. It itself is a random variable. It itself has a distribution. That's so important to realize this. Emphasize it's got a distribution by calling it a sampling distribution. It's a distribution that comes from a random sample. The central limit theorem says when n is large, it's approximately normal. But we saw when n is small, we did figure out the distribution of this. For example, we did an example where the population distribution was uniform on 0, 1, and we figured out the distribution of x1 plus x2 over 2, the sample mean, and it was not normal. It was a triangular shape. Remember doing that? Triangular distribution. How did we figure that out? We did some integrals. Will integrals show up on this exam? No. But we did do that before. But it is a statistic. And in chapter 7, we also learn it's an unbiased statistic, though I did mention that before we got to chapter 7. The mean of the mean is the mean. Expected value of X bar is mu. We also saw the variance of X bar was the population variance divided by n. The variance of the variance is not the variance. Shouldn't say the variance of the variance. The variance of the mean is the variance divided by n. The theoretical variance of the sample mean, which is a statistic, is the population variance divided by the sample size. And it's a good thing we divide by the sample size, because that means when you have a bigger sample size, this gets smaller. Being unbiased is not enough to guarantee that when you compute X bar, that it's close to mu. It just means over many, many samples of the same size, random samples from the population, about half the values of X bar will be less than mu and about half will be bigger than mu, roughly speaking. The sampling distribution is got a center of mass at mu, and if it's symmetric, it's centered on mu. We also have the sample variance, capital S squared. The summation, capital Xi minus capital X bar squared over n minus 1, because we lost a degree of freedom. Don't worry about what that means. It's technical. It is unbiased. The expected value of S squared does equal sigma squared. The mean of the variance is the variance. But S, the sample standard deviation, is the square root of the sample variance. That's not unbiased. You should know these things for true-false questions, or maybe multiple choice. Unfortunately, that's not unbiased. It's biased. But we live with it. Then we moved on to chapter 7. Well, this is partially chapter 7 here. Continuing in chapter 7. We got into some pretty heavy theoretical stuff. Probably the easiest of which was the method of moments, MOM. Though that was still tricky. It's easiest to think about with examples. Simplest examples include geometric, binomial. The really simplest is Poisson. You should be able to apply the method of moments. You take a theoretical fact about, for example, the geometric distribution, that the expected value is 1 over p, and you replace these theoretical ideas here with statistics. Expected value of X bar gets replaced with the first moment. You could call that M1, but more commonly call it X bar. You should feel comfortable with calling it either thing. Replace P with an estimator, P hat. Solve for that estimator. There's not much to do. P hat's 1 over X bar. Done. Do similar kind of things for binomial and Poisson. With the Poisson, there's really nothing to do. The expected, besides just replacement, expected value of X is K. So X bar equals K hat. Done. No solving necessary. K hat equals X bar. The hardest example was the gamma. That involved the 2 parameters, alpha and beta, and 2 equations involving expected value of X and expected value of X squared, based on the formulas for the mean and variance of a gamma. You had to replace expected value of X with M1 and expected value of X squared with M2, alpha with alpha hat, beta with beta hat, solve for alpha hat and beta hat. It's a system with two equations, but it's doable. And you should be able to apply it. We're running really low on time. We also had maximum likelihood estimators. That was harder. We were trying to maximize the likelihood function. Easier to maximize the log likelihood function. Be able to do it in simple cases, geometric binomial Poisson especially. The book does it in the normal case, but that involved partial derivatives and it was too complicated, I think for us. Be able to also apply it if I give you particular numbers instead of just an arbitrary random sample x1 through xn. Then we had moment generating function stuff. There's the fingerprint theorem. We're going to go a little over here. Fingerprint theorem said if two moment generating functions are the same, then the variables have the same distribution. We got the theorem about the MGF of the sum of two independent random variables or more independent random variables is the product of their moment generating functions. And so, you know, it's really here in exam 3 where the tables in chapters 3 and 4 are really the most useful. Because then you can look up the moment generating functions, you can multiply them, simplify it, use the fingerprint theorem to identify the distribution of the sum. A homework problem related to chi-squared distribution, for example, with that. We did apply the CDF method a little bit more in chapter 7 as well. Maybe that could come up. Then we have the central limit theorem. Started talking about, this continues in chapter 8. Confidence intervals on a mean. We also actually did confidence intervals on a population variance. And from that, by taking square roots of confidence intervals on population standard deviation, we had to use the chi-squared distribution. Remember that? And then hypothesis testing stuff. On a mean. And then chapter 9, what we talked about for the most part today is proportions, confidence interval, sample size necessary to get a margin of error, and hypothesis test.